Good morning, Cece. How are you?
Good morning, Nicholas. Good. How are you?
Good, good, good. Let me
Great.
just I have to grab my hot water. I'll be right back. All right, good morning, guys. I see Trevor is here. Hello, Trevor. Go Phillies. Ven is here. Hello, Ven. Devin, Angelo, excuse me. Andrew, Hector, Kaji, good to see you all. Little question I want to ask you all to start off. I'm curious, has spring come to your part of the world yet? Is there green around? Is it just raining? Let me know. What do you think? I'm curious. We're spread all across the world here, so then can maybe report on the San Francisco, Alabama weather. Green shoots, love it. Days are getting a little bit longer, and we also had that big time change this weekend. Nothing's better than waking up an hour earlier on Monday. Am I right, guys? Leftover snow from Andrew. I'm sorry, Andrew. Bummer. Trevor's back in the cold. Oh, well. Things are getting hotter in Florida. They do tend to do that in Florida. Florida has just beautiful winters, but yes, the summers can be rough. South Florida, awesome. Kadia said Florida is in summer right now. There you go. It's always summer in Florida. My grandparents, they lived in Boston all their lives, and then they retired to Florida, or some sort of, basically a suburb of Boston that was in Florida somehow. I don't know how it worked, but my grandfather used to drive around, and he had this golf cart. It had his name on it. It was like the greatest. It was like summer camp every day for him. He loved it. Logan is here. Hello, Logan. Zunaira, good to see you as well. Eric. Let's give it one more minute and then we'll get started for today. I hope you all had a restful weekend, ready to tackle Big Sprint 2. All right, let's get started. I'm going to share my screen with y'all, and then we will jump into all the cool stuff that we get to do today. I have to say that Sprint 2 is my favoriteest sprint of the whole unit, and so I'm glad that we can kick it off. The highlight of my month. All right, so today we call this sprint the Kaggle Challenge sprint. And the reason we call this the Kaggle Challenge sprint is because this week we have a Kaggle challenge. So Kaggle is a website where people do all sorts of data science competitions. So where you download the data, you might have some insight into the data. There might be some notebooks to work on, but then eventually what you do is you use that data to build your own model and make your own predictions. And then you upload that data to Kaggle and you will see how you are doing. So what I want everyone to do is set a goal for themselves to do at least one submission to this Kaggle competition put that model out into the world, put your predictions out into the world, and we'll be evaluating everyone's models using accuracy. That's our test metric of the week. And the test data, you'll only be able to see your score. It's calculated using only 50% of the test data. And then at the end of the week, Friday at noon, Lambda time, we'll drop the other half and you'll get to see your final scores. So throughout the week, now is the time to start building your model, and we'll learn all sorts of tools this week to kind of improve your models along the way. So even if you want to do every day, do a model, that would be a great place to start. And for those who did 60-minute models on Friday with CC, there's a great kind of hands-on tutorial about how to use Google Colab to generate those predictions, generate a CSV file, and then upload them to a website like Kaggle. All right, back to our presentation. So we're going to be learning about a new type of model this week. And one thing that we kind of hinted at last week is that linear models are very wonderful in the sense that they're very interpretable. You know, you have these coefficients, they're either positive or negative. You know how they are influencing your predictions. But those linear models are very strict. Everything is a question of lines or a question of planes or a question of cubes or hypercubes. It's always thinking in straightness, linearity. And what we're going to be learning about today is a model that doesn't work in those terms. It's a much more flexible model. So in that way, it's kind of wonderful and fantastic. However, what we're also going to learn that with this great flexibility comes something called overfitting. So we're going to talk more about that today and start kind of really diving into the question of overfitting. So with great flexibility comes great overfitting. In terms of what we'll be doing this week or this sprint, we're going to be focusing on a much larger, messier data set than we've seen before. So we'll do a lot of wrangling. The other thing we'll be doing is we'll be building new models, building those tree-based models that I alluded to just a second ago. In terms of metrics, you know, for classification, so far we've been using accuracy score, but we'll be looking at new metrics as well, namely precision and recall score. And if we get to it this week, we'll also do ROC, AUC, but we might get to that on next Monday. So we'll see how that works. And then we'll be talking a lot more about hyperparameters and how to tune your hyperparameters. So we really have been kind of skipping over that step in the previous sprint, but now we're really going to dive into it headlong. So get ready for that. In terms of what we're doing today, we'll be focusing on wrangling our messy data set and on building our model. Our goal is we want to create a model that's going to predict water pump status, whether a water pump is functional or not, or whether it needs repair in Tanzania. And in order to meet that goal, we're going to have to check off a few objectives along the way. Namely, we're going to need to clean our super messy data set. We're then going to need to use scikit-learn to build a decision tree model. And then I want to talk about how you can get and interpret feature importances for a tree-based model. So not talking about coefficients and plotting out those coefficients, but rather talking about feature importance. So those are our goals for today. In terms of my personal battle plan, we're going to start with a lot of exploratory data analysis to define our problem. We're going to clean our data set. Then we're going to build that decision tree model and then get the feature importances from that model. And we'll learn about what decision trees are and how they work as well along the way. So that's my plan. And now let's get started. So what I'm going to do is I'm going to remove this slideshow. We don't need it anymore. And I'm going to go to the guided project notes for today. And of course, as always, I will be sure to share these with you after class. So let's get started. The first thing I'm going to do is I'm going to run this preamble here. And notice that I'm installing two different things into my environment. First, I have category encoders, our dear friend category encoders. And the other thing that I'm installing is something called Pandas profiling. which helps you get a better sense of what might be some possible issues with your data set. So those are the two guys that I'm going to be installing today. So I'll run this. And while that is installing, let me just quickly look at the other libraries that are going to be in our arsenal today. The first is we're doing category encoders. Note, however, that we have not only one hot encoder, but we also have the ordinal encoder. We have our profile report, which I just spoke about. We have our simple imputer for filling in those missing values. We have our old friend, the logistic regressor, which we'll be using to compare with our decision tree. We've got train, test, split to do our splits. We've got our pipeline to make our pipeline. We've got our standard scaler, another transformer that's really helpful when you are working with logistic regression. And then this is the fun part. We have the decision tree classifier. That's the new predictor we'll be using today, along with plot tree, a way to visualize that classifier. And then we'll also have matplotlib and pandas. All right, so that is our plan. Let me just run this so that everything is in my memory space or my namespace, and let's get started. So the first thing that I am going to do is we need to find the data path, and let's see here. We have here the data path, and the next thing that we need is the file. Hold on one second. We need the files that we're going to be dealing with today. So let's grab those. Give me 1 second. Let me just pull out my notes for today. Here we go. So the file path is going to be water pumps. Let's see here. Let's actually check this out. Let's go to the GitHub repo and check it out. So I'm going to go to GitHub, Lambda School. I'll do DS unit 2, not linear models. I want to go to, let's see here. Let's see what we can find. Let's actually just go here. We have linear models, we have statistics. Here we go, a Kaggle challenge. Here we go. Let me share that with y'all. Let me unlock the notes as well now. Give me 1 second, guys. I thought that I had unlocked these. One thing to keep in mind is that you can also make sure that you're linked if you are, there we go, that link should now work. If you are logged in with your Lambda account, you should always be able to see these notebooks. So if we go here to the Kaggle challenge and we look at data and we look at water pumps, we can see that we have 4 different files here, and they're all CSV files. And we don't need to worry about sample submission right now. The thing that I want to highlight is that we have both train features and train labels. So that means, like in the Titanic data set that we saw on Friday, our feature matrix and our target vector are actually already separate here. So that's one thing we need to keep in mind. We probably need to put them together in order to start. So let's, before we do our wrangle function, let's begin thinking about these data sets in general. So let's just do, let's see here. Let's say df equals, let's do it this way. I'm going to use PD merge here because I know that I have my target vector and my feature matrix as 2 separate things. And then inside them, what I'll do is I'll do PD read CSV. There we go. And I'll have 2 read CSVs here. And the first read CSV is going to have the data path with our features. There we go. And then the second one is going to have the labels. There we go. And so if I run this, what we'll see is we can begin thinking about how we're going to work with our data. So what do you guys do when you first run into a new data set? What are going to kind of be our go-to commands for beginning to explore what's going on with this data set? DF head is a big one. What else? Devin's got a good one. Info, shape, describe, is null. These are all good ones. I always like to start with DF shape because it gives me just a very quick idea of what we're dealing with. And I can see here that we have 59,000 rows and 41 columns. So we're finally getting into kind of a bigger data set here. It's pretty long in terms of the number of observations and pretty wide in terms of the number of features. If we wanted to take a look at what those features were, we could do it this way. Notice here that we have ID. That looks like it's pretty important. And we have a bunch of other stuff. And the one that we're going to use to predict here is called status group. And we'll look more at that in a second. But let's also take a look at DF head and begin thinking what's going on with these data. So here we go. We have a good idea of these data. Notice that we have longitude and latitude. That's going to be very helpful. We definitely have both text data or categorical data, and then we have this numerical data as well. So this is all going to be helpful stuff. And the question is, how do we start wrangling this? Well, a lot of the things that you guys have mentioned all definitely work. But one way to deal with like a big messy data set that you have is you can use something called pandas profiling. So let's pull up pandas profiling, say that 5 times fast, and let's see how this might help us. Okay, so what I'm going to do first is I've already imported, if we go up to the notebook here, I've already done, let's see here, where is it? Pandas profiling, I've already imported profile report. And so what I'll then do, if I scroll back down, there we go, is I will do, let's see here, profile report, and then I'm just going to put in my data frame, and I'll do a couple other things here. I'll just do, let's see here, minimal equals true. And I wonder if this is all I need. Let's see here. I think this will give me everything I need. Now, one thing to keep in mind is that this is a great resource to have when you're looking through a big data frame. It is, however, not a very good citizen of the Python universe. And so you might find if you're working on Colab or if you're working locally, you might have some troubles getting this to run. So just something to keep in mind. And the reason that I love is it tells us all sorts of different things about our data. For example, CT was interested in null values. Well, here I can see that we have about 2% of our observations or of the data is null. It looks like we don't have any duplicate rows, which is very good, although we should look at columns as well. And we can also see the breakdown of variable types. Now, if you wanted to, you could go through every single variable here, and it gives you some idea of the different distributions of those and maybe some warnings. But what I really like to do is I like to go straight to this warnings. And this gives me a good idea of if there are any big issues that I need to deal with in my data set. So let's start with number 1. I can see that recorded by has a constant value of Geodata Consultants Limited. What does it mean when it's constant, and what should we do with a data frame that is, or with a feature that is constant? So Joseph, Logan, and Trevor are saying you got to drop it. You got to drop it like it's hot. And that's indeed what we're going to do. So let's start building a wrangle function around what we see here. All right, so we have a wrangle function. And I think what we need to do is let's create a wrangle function. We know that there are 2 data frames here, or 2 CSV files. And so I think we actually need 2 different targets. So I'm going to have 2 different not two different targets, two different variables that we're going to input. So let's have the feature matrix path, which we'll call FM path, and let's have TV path or target vector path. All right. And then what we can do is we can just take this here and pop it in. There we go. And then let's just change this to TV path and FM path. There we go. Okay, beautiful. And then one thing that we're going to need to do is we'll do, let's see here, df drop columns, and we'll drop recorded by. Let me just make sure that's right, recorded by, okay. And here we can say we'll drop constant columns. Okay, beautiful. All right, and then let's just turn df into wrangle. Actually, let me do it this way. df equals wrangle. And here we'll put in the first path and we'll put in the second path. And that should give us exactly what we want. And since this is such a big data frame, let's only look at df.shape. So we should go from 41 to 40. Okay, there we go. Oh, now why did this not go to 41 like I wanted it to? Or why did it not go to 40 like I wanted it to? Why is this not dropping? What's wrong with my code here? Logan, you've got it. Exactly, guys. I got to go in place equals true. So that's the issue. And if I do this again, now we're back where we need to be. Okay, beautiful. So the next thing that we need to do is we have a bunch of columns here which seem to be high cardinality, high cardinality. So what should we do with these high cardinality categorical columns? What do we normally do with these high cardinality categorical columns? So Nara is saying, usually we drop them, then and Logan agree, and that's absolutely right. We should probably drop these. We probably also need to think about, we need to think a little bit about some sort of cutoff. So let's do this the way that we did it last time. I'm going to move through this a little quickly, but I'll do df select dtypes, and I'll say, give me object. And what that will do is it's going to give me all of the columns that are categorical. So here are the categorical columns. And if we look at n unique, there we go. That's probably misspelled. Much better. So actually, wait, I need to do it like this, not columns. There we go. Beautiful. And so this gives me a good idea of what are my high cardinality categorical columns. Let's actually sort these values. There we go. So here are really the columns that I need to worry about. Beautiful. Andrew's saying they have no sound. Can other folks hear me? Give me like a thumbs up if you can hear me. Okay. So Andrew, maybe what you can do is leave the room and then just come back. We'll be here waiting when you come back, I promise. Okay. So how can we drop all of these? How can we be sure that we're dropping only the columns that we want to drop here? How did we do this last time? One option is we could just, write them in by hand. That's a possibility. But probably we want something like drop calls, and we created a list. So I could do it like this. I could do a list comprehension. And what I could say is, let's say I take this here, and I'll put it here. I always use my list comprehensions. I always start from the back. So this is going to be the thing that I'm going to iterate on. So I'll do call for call in df select type dtype columns. And now if I look at drop columns here, these are all of them, but I want to only drop a certain number. So I'm going to add an if statement. So I'll say if df call dot n unique is more than, and let's set a cutoff here. Let's say the cutoff is 100. There we go. Beautiful. And so here are the ones that we need to work with. So let's use these. Okay. Now notice here that I'm dropping the date recorded. There might be valuable information in here. For example, you might want to create a feature. How old is a pump? So think about how you might do this in your own wrangle function. I'm going to leave this kind of simple as is, but that definitely might be how you want to, something you want to explore when you move on, as you move on in the competition here. So what I'm going to do is I'll go up to the wrangle function, and my next step will be drop high cardinality categorical columns. High cardinality categorical columns, HCCCs. There we go. And then I have to be sure to drop those. So I'll do df drop columns equals drop calls. And this time I won't make the same mistake twice. I'll do in place equals true. There we go. And now we'll see that I go from 40 down to df shape. Whoops, I got an error here. Unexpected keyword argument columns. I'm not going to lie to you guys. I was in the orange group in spelling in the 4th grade. I have since learned that orange was the group for students who are not good spellers. All right, so now we have 32 columns. Now let's go back here and let's see what else we have. We also have a lot of, let's see here. Look at this. Look at GPS height. Look at longitude. Actually, this is interesting. Longitude as a 0? Huh. Let's look at something here. I'm going to remove this here, and I'm going to just do a regular old scatter plot. Let's do PLT scatter, and let's think about longitude and latitude. There we go. And let's just see what this is. Let's take a look at our data. Now here we can kind of see a blob that looks like Tanzania. It's a little bit squished because of the X ticks, but this is generally what Tanzania looks like. But then we have this thing over here. Now, what's the deal with these zeros? What do you think is going on with our data set? So Joseph's theory is that we're missing location data. All right. Now, this actually is a well-known phenomenon in location data. where you get a bunch of locations at 0, 0, and we actually call this null island. So just a little geodata joke. All right, so we have this null island. We know that there are a bunch of data points at 0, 0. How should we keep them at 0, 0? How should we deal with these? So one thing we can do, and Carlos, I think you're right on the money, is that we can think about maybe coding them in as NaN values. And you know, it's funny when we're looking at all of these things here, like GPS height, number of private, population, I suspect we are going to make an educated guess and say, well, maybe we can treat these all as null values. And so one thing that I can do here is, for example, in my feature matrix path, there is a, let's see here, NA values. So I can put this in as a 0, and that should solve the problem. Everything that's a 0 in our data frame will be coded as NaN. Let's do a little bit more exploring, though. I want to just look here and see, let's see here. Let's do a filter. Let's do DF, and let's look at DF latitude. Let's say it equals 0. Let's just look at the head. Oops, that's not right. Let's look at DF. Maybe it's longitude that's at 0. I would think that they were all at 0, right? Because it says 0, 0. Let's try again. Look at this. Look at this, guys. We found this out. So here we have longitude, and they're all at 0, but at latitude, we didn't see anything at 0, which was kind of weird. And it looks like these have been recorded in some very, 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 very tiny negative number, basically a 0. So in fact, we have two types of zeros here. We have the regular old float that's a 0, and then we have this tiny, tiny negative number, which is also going to be a 0. And going to Curtis's idea, notice that all of these seem to be in the Lake Victoria Basin. So what you might want to do, you might see if this works for your data, for your model performance. You might think about, is there a way that I can impute, like can I find the Lake Victoria Basin and impute those values specifically? Or can I find out where the Shinyanga region is or the Mwanza region is? Excuse my pronunciation. So that might be a good option. But for now, let's keep it simple. The idea here is I'm going to keep things simple today, and then you all can kind of make it more complicated as you move on in the week. So let's do that. There we go. And now if I look at my shape, this will be the same shape, but we'll see a big drop in terms of the null values. In fact, if we plot this out, we'll see that there is no longer a null island, and we can see a little bit better. Now this is like squished the other way, but it still generally looks like Tanzania. So we've removed those null values. Beautiful. And let's see here, what else do we need to do? What about ID? Now, is ID a feature? Is this something that our model can use to make a prediction? I see Logan is shaking his head. What do other folks think? Carlos is saying it needs to be the index. I think I agree with that. So why don't we just if we go up here, let's do set index, or sorry, I think it's index column. There we go, index column equals ID. This is already looking good. Okay. Beautiful. Whoops, I got an error here. No common columns to perform a merge on. What do you think is this problem? No common columns to perform a merge on. What's happening? Why did this work before, but as soon as I set the index column to ID, it stopped working? Carlos is saying maybe both data frames don't share an ID feature. Well, I mean, that's possible, but it worked before. And Ven is saying, well, maybe the index column was the primary column for the merge. And when we put it as the index, it was no longer in the data frame. So if we did something, for example, like we did it for both of the data frames here, now, whoops, hold on. Now it continues to not work. Oh, you know what I think the issue is? Let's do it like this, actually. I have an idea. I think the best way to do this is, instead of doing this in the whole data frame, what if after we created this merge, so after the merge, we did set index to ID. There we go. Excellent. So now we should have 31 columns. There we go. Beautiful. And now if we look at df.head, things should already be looking a little bit cleaner. Excellent. We can see we have our null values are here. We have our null values here. Beautiful. Okay, this is already looking good. I'm already very happy about this. Excellent. All right, let's do one more thing, which I think is important. We know that we only have, we know that we don't have any repeat rows, but with a data frame this wide, it's generally a good idea to check if you have repeat columns. So what are some ideas you guys have for how to check for repeated columns or duplicated columns? So now we're going up and down feature-wise, not side to side, observation-wise. So how do we check along this axis versus what we've been doing now until this axis? And we don't need code. If you just want to throw out your ideas, I would love to hear them. We can look for similar feature names. That's a good idea. So we can look at columns, df columns, and we can see, for example, that we have water point type and water point type group, quantity and quantity group. Let's check this out. Quantity and quantity group, let's look at head here and just see what it looks like. And it looks like, indeed, you're right, Logan. It looks like we have these quantity groups that seem to be the same. So that's one issue. So for example, I could say drop quantity group. Another thing I can do is, for example, I can take df.head, not df.dead, df.head. Let's just take the first, say, 15 rows. So here are the first 15 rows of the data frame. And whenever you want to take a data frame and you want to turn it on its side so that the rows become columns and the columns become rows, you can use a capital T, T being for transpose. Now, you don't want to do this with a really long data, with like a really big data frame. It will be it's very computationally expensive. And that's why I'm only doing the first 15 rows. I wouldn't do this with all 40,000 rows or whatever it is. So if I do it this way, though, I can see now I have my data set transposed. And then, you know what I can do is I can do duplicated. There we go. And what this tells me then is precisely what Logan was saying. It looks like quantity group and extraction group are repeat columns. I'm not sure about water type and water type group. I'm going to let you guys explore a little bit on your own. So let's see here. If I do, let's see here, duplicated. And let's just filter this to true. Or you know what I could even do? I could do drop. These would also be drop, not columns. No, these would be more columns, right? So I'll call these dupe columns. And I could do another list comprehension. So I can say call in df.head. Actually, I guess this would be, let's see here. This would be, let's do duplicated index. There we go. Here they are. And I can do another thing here. I can go if, let's see here. Oops, I got an error here. Invalid syntax. I don't need this comma. There we go, beautiful. And so what this is going to do is it's going to say, give me every column in this series, but only if that series, if I look at that location, if it equals true. And I don't need to even put this here because it will just evaluate to true or false because I have these true false values. So I can take this and I can pop this in here. So I can say drop duplicate columns. And I can paste in this guy. And then just do the same drop that I did before. And if I wanted to, I could take all of these things and kind of put them all together at the end instead of doing all of these drops individually. It's kind of a question of style in this case. So I have my dupe calls and I have my drop calls. There we go. So now if I look at my data frame, I should now go to, let's see here, we were at 32 previously. So now if we look at DF shape, we should be down at 29. Beautiful. I guess we were 31. And now our data frame is looking pretty darn clean. Excellent. I'm already feeling good about this. Beautiful. Okay, so here is our wrangle function. Any questions about anything we've done now in getting our data ready to work with? Or anything else that folks want to explore? All right, then let's leave it there. Let's take our first break. And when we come back, let's put together our pipeline. No, let's put together our baseline and just kind of see where it goes from there. See how things develop. All right, see y'all in 5 minutes. Okay, come on back, guys. Time to rock, time to roll. You know, I saw a movie this weekend. My wife and I, we went to a drive-in where they had the big screen. You could just be in your car. We saw that new Disney movie, the Aquafina movie, where she's like a dragon. We were definitely the only people there without kids, I have to be honest. But my mom really, excuse me, not my mom, my wife really likes Disney movies. And then I told my mom about it the next day and she made fun of me for going to a kids movie. Okay, but it's pretty good. Recommended. I don't know. Have y'all seen it? Raya. Thank you, Carlos. That's what it's called. Raya. It's pretty good. Okay, before we forget, let's do our attendance quiz. I just dropped the link in the Slack. And today's lucky numbers are 6001. I'm going to do my best. Let's see here. 6001. Okay, excellent. All right, 6001. And now we are ready to dive back into our data set here. So we've already done a lot of wrangling. We have lots of good stuff in this wrangle function. I love it. So first of all, we merged together our data frame and our feature matrix and our target vector. We also dropped columns that we don't need. We took care of this cutoff. We also looked at duplicate columns. Beautiful. And so it looks like we're doing pretty well. I'm going to delete this profile report because I don't think we need it anymore. But one thing I do want us to do is I want to be able to, since we are using this, I want to make sure that it works the same way for our training data as it does for our test data. So let's just do a quick comparison here. So I have my data path for the test data. So I'll just call this X test and I'll do wrangle and then I'll drop in this. And let's just see if it gets us the same thing. Okay, and I get a type error. Now I can see that it is the line I just added making problems. And it says wrangle missing a required positional argument, TV path. So what's going on here? How can we fix it? Why am I getting this error? So Venn is saying the function is expecting two arguments, right? We need two arguments. Andrew, you're right. It wants target vector and feature matrix. So how can we change our wrangle function so that it works within these constraints? Because we want to be able to clean our data the exact same way. However, there's going to be some differences here, right? We know that one of our things that we're going to be loading is going to have two pieces to it. And we know that our test data is only going to have one piece to it. So how can we fix this problem? Curtis is asking, can we still load the training labels? I mean, I suppose we could, but the thing is that these training labels are not going to be relevant to the test data. And also the test data is smaller, I'm assuming it's smaller. So how can we do this? And if I do X test dropped target, well, I could do something like this, and I could say drop, columns equals whatever, pump status. Let's try that. Let me just comment out this first one so it doesn't take so long. And we still get that same error. It's not going to help us here. So how can we have, basically what we have is we have this problem where we are loading two different kinds of things into the same function, and we need our function to be able to adjust. So how do we deal with this kind of program flow when there are kind of two paths to take? Now I see Venn has the idea of an if statement. What do you guys think? Let's give it a try. So one thing that we could do is, you can always put in defaults for these arguments. Like if I don't give you an argument, then what you can do is just use the default. So for example, here I could do none. And I could do something like if TV path, and I could say not none. Or actually what I could even do is I could just do it like this. I could say, all right, do this. Let's just see if that works. Let me try it with our test data first. Okay, it works with our test data. Beautiful. And then the other thing I can do is I can say else. And then what I can do is just say, I'll do df equals, and this time I don't even need to do the merge. I would just do read CSV. There we go. Read CSV. Beautiful. And then I can also, here I don't even need to do it outside this call. I can just do index call equals ID. There we go. Let's see if that works. All right, it looks like it does. So now if I look at xtest, if I look at xtests.shape, I can see that I have 28 columns. And if I look at df.shape, I have 29 columns. Does that make sense? What's the difference? What's the one difference? What's that 28 versus 29? It's the target. The target is a withheld. I love it. So we've got that. Let's just also make sure that the columns are correct. So I'm going to look here at xtest columns. There we go. Let's just see if that equals df.columns. Oops, I got a true here because there we go, misspelled it. Length must match to compare. So if I df columns and I did df, let's see here, drop columns equals status group. There we go. Okay, beautiful. So it looks like now we have the exact same number of columns, so we're ready to go. Okay, beautiful. So we've done this now. Our model is now, our wrangle function is growing, but it continues to work. And the next thing that we need to do is we need to split our target vector. We need to we move on to phase 2, which is splitting data. And we need to split our target vector from our feature matrix. You know what, I should probably do, I like using X and Y first, so use it that way. There we go. I'll run this. All right, beautiful. And so now I have my feature matrix, big X, and my target vector, little y. And then the other thing that I want to do is, because I cannot see how my model performs against the test data until I make a submission, and because in the Kaggle competition, I can only do 2 submissions per day, I want to make sure that I have some estimate, some way to estimate more or less what the performance of my model is going to be. And so I'm going to use a validation set. And so I'll use the train test split that we did on Friday or Thursday, I can't remember, but I'll have the test size as 0.2 and I'll set the random state as 42 so that it's reproducible. And that should give me a good sense of, let's just see, let's look at X train. I can see I have 47,000. If I add that to the length of X val, I have 59,000, and that should equal the length of X total, and it does. Okay, beautiful. So I know that my data is correct. And so once I've done this split, I need to establish a baseline. Now, let's take a look at our target here. And if I look at X train, or rather, if I look at Y train, and I look at value counts, I can see that there are 3 different possibilities for our target. I can either say that a pump is functional, I can say that it's non-functional, or I can say that it's functional, needs repair. So is this a regression problem or a classification problem? Carlos is saying this is classification. Andrew and Zunera are also saying that. And so, okay. And is this a binary classification problem or a multi-class classification problem? So binary, multi-class. So an example of binary would be like yes, no, true, false. And in this case, since we have 3 different discrete values, functional, non-functional, and functional needs repair, this is an example of a multi-class. So you're absolutely on the money there, Eric and Andrew. Okay, beautiful. And so the question then is, if our model, if our baseline model was always going to give one single prediction, what would the prediction be? Like if you could only do one prediction or one guess, what would it be in this case? And I see Andrew and Curtis are saying functional. Why are you guys saying that? What's your thinking? Majority rules. I like that. Majority rules. Another way to think about this is you need to always look at your, we call this the majority class, the majority class. So in this case, functional is our majority class. And if we look at normalize and we set normalize to true, we look at the normalized counts, we can see that functional accounts for 54% of our training set. So if we always guessed functional, we would be right around 54% of the time in terms of our accuracy score. So our baseline accuracy score is going to be 54%, and that's what we need in order for our model to work. Okay, beautiful. So we've split our data into feature matrix and target vector, and then we split it again into training and validation sets. And then we established our baseline, which in this case is an accuracy score of 54%. So now we need to move on to building the models. So let's build two different models. Let's build our logistic regressor, and then we'll build a decision tree classifier. And we'll evaluate how they work, but I also want to talk about how a decision tree works. So we'll look at their performance, but then I want to go back and talk about how a decision tree works. So let's start here with make pipeline. And let's think, before we kind of move into our data set, or before we move into our model building, what sort of issues do we need to deal with? What sort of things need to be in our pipeline? If we're looking at, let's look at, let's see here, xtrain.info. What do we need to make sure is in our pipeline? So Curtis is saying we need a one-hot encoder for our categorical variables. So we definitely need some sort of encoder for categorical variables. And then we need an imputer for missing values. Beautiful. And then there was another transformer which is good to use when you're using a logistic regressor, and that's going to be the standard scalar. For logistic regression. Beautiful. Okay, excellent. All right, excellent. So now we know what we need for our model. Let's start putting it together. So the first thing I'll do is I'll put in my one-hot encoder, and I'll use cat names equals true. Okay, and then the next thing I'll need to put in is my simple imputer, and I'll just use the imputation. Right now, the strategy, the default is mean. So I'm just going to keep it as mean for now, but I want it to be explicit here. So I'm just going to type it in. I want the next coder who comes after me to know what's going on. And then I want to put in the standard scalar, since this is a logistic regressor. And then finally, I'll put in the logistic regressor itself. So this is going to be the model. And let's do model LR dot fit. And I'll use xtrain and ytrain. Beautiful. Okay, so I've got this set. This is ready to go. Any questions about this pipeline before we put the training to work, before we start training? So Ven says, are there no hyperparameters? There are hyperparameters. For example, here, the strategy that we're using to impute missing values, we're using the mean. We could use the median. So that's an example of a hyperparameter that we set. And we're not going to worry too much about hyperparameters now, but that's sort of one example here where I would definitely be thinking about hyperparameters. But we'll talk a little bit more as we move on. So I'm just going to run this model here. It'll take a second to train because it's a good amount of data. There we go. It seems like it's very unhappy about the number of iterations. So whenever you see this and you're using a logistic regressor, basically your data is having trouble. It's having trouble getting to kind of like conclusive answers as to what the coefficients should be. So one way to deal with this is to change here the number of iterations. You can set this to a bigger number like 1,000, but I'm actually just going to ignore this warning for now. I want to see what our model performance is before I waste everyone's time training a model. So I just want to see what our score is going to be for our training and our test. Notice here that I'm using the dot score method because the default score that you get when you do dot score for a classifier is you get accuracy score. So we're hoping for an accuracy score, which is good. And we can see that our accuracy score, two things. One, we can see that the performance is almost exactly the same. So we have 73%, 73.8%, and 73.6%. So we don't have any overfitting. And we can also see that our model is beating the baseline if we look at the validation accuracy. So this is very good. This is very good news. So the logistic regressor we learned last week could definitely be helpful here in terms of providing value to solve this problem. Okay, so let's see here. I want to get your thoughts on something, guys, before we move on. Would you rather that we built the decision tree model first and saw how it performed? Or would you rather that we talked about what a decision tree is and how it works first? Do you want to do the implementation or the concept piece? What would work better for your learning styles? I'm curious. Kaji wants me to kill two birds with one stone. I can't, but I have to draw, you know, and I can't draw and code at the same time. So given that limitation, what would you say, Kaji? All right, I can explain it first. All right, let's explain it first. So let me just share my whiteboard with you all. And let's see here. There we go. I will now share this. This will suddenly become all black. And then we will go back and make it work again. And here we are. Okay, beautiful. So just as a quick reminder, when we were talking about linear models, remember that linear models are linear because they always think in terms of lines. So if you have data that looks something like the data that I'm putting up in front of you now, it's very easy to fit a line to. And so a linear model is going to be really good at dealing with data where you can describe the relationships between your features and your target linearly. However, that linear model really begins to fall flat on its face when you have nonlinear relationships. Let's say that my data looks like this for the first part, but let's say that actually for the kind of the second part, it looks like this. Now, a linear model is going to have a very hard time dealing with these data because it's not going to know whether it needs to go this way. Oops, hold on. It's not going to know whether it should go this way or whether to try to kind of split the difference and go this way. But either way, it's not going to be very helpful. So what we need is something that's going to give us an ability to fit to these data in a way that is not limited by thinking in terms of straightness. Geometric straightness, I should say. So enter our new friend called the decision tree. Now, let me ask you guys a question, and you don't need to answer, but I am curious. Have you ever been at the shopping market, or as it's also called in English, the supermarket? I don't know why I called it the shopping market. And you're in the checkout line, and you pull a magazine down from the rack, like a Cosmo or some sort of Cosmo magazine, and you open it up, and there's like a quiz. And the quiz is always like, oh, are you an introvert or an extrovert? And you kind of start off at one square and it says, oh, do you like talking to other people? If yes, go here. If no, go here. And then maybe you have another yes, no question and a other yes, no question. And you learn that not only are you an introvert, but that you also are you go best with autumn colors. And that's what you should be looking at this fall. So has anyone taken this sort of Cosmo quiz? All right, I see Carlos is. Oh my goodness, Andrew's talking about goosebumps and choosing your own ending. I also think this is like a choose your own adventure kind of thing as well. So really good point. Excellent. So you can think of it as a choose your own adventure. You can think of it as there are lots of different ways to think about it. But the idea here is that you're kind of following a path. Well, that's exactly how a decision tree works. So let's think about our decision tree. Let's start at the top here. And the way a decision tree works is you start with something that's called the root node. And with the root node, we have all of our data points in the root node. So let's say here that we have our functional data, we have our functional needs repair data, and then our needs repair data. So we have all of our observations kind of lumped together in one particular node. Well, the way that a decision tree works is that it's going to look at all of those data and it's going to look at all of the features. So all of those features, and it's then going to look at cutoffs. So for the numerical features, it might say GPS height, more than 100 or less than 100. Or for something categorical, is this in the, I can't remember the name of the valley. Is it in this water basin or is it not in this water basin? And so what's going to happen is it's going to look and try to make some sort of yes/no question. And then based on that yes/no question, it's going to subdivide the data. And the goal of this model, you might be asking, what are the criteria that our model is using in order to subdivide this data? And what it's trying to do is it's trying to find the best feature and the best kind of cutoff where in the subsequent nodes that come next, we call these maybe child nodes. These nodes are more pure than the nodes that come above them, than their parent nodes. Or another way to think about it is there's less of a mix of things. So for example, here we can see that it's been able to create a more pure node because it's only now has these two groups. So it's trying to go through all of those features and find which feature and which cutoff for that feature will result in two child nodes that have a higher level of purity or a lower level of impurity than the node above. And it will keep doing this as long as it needs to until it ends up with basically 100% pure nodes. Oh, I changed green there. I'm not sure why. Don't worry about it. So here we might end up with something that looks like this. And maybe we might find that there needs to be an additional node here just to do that final split so that everything ends up ship shape. That is another green. Beautiful. There we go. So this is what our decision tree looks like. So we're going from that impure root node to these 100%, we call these either terminal nodes or, since these are called decision trees and this is the root, we can sometimes also call them the leaf nodes. So we go from the root node all the way down to the terminal nodes. And you're saying, is this a tree? And I guess it is if you turn it on its head. Even then it kind of looks like a bush, but a decision bush is not nearly as compelling as a decision tree. Now, as your tree grows, what it adds is depth. So for example, this tree has a depth of 3 because it makes one set of splits here, it makes a second set of splits here, and then the final set of split, or the final split down here. So this tree has a depth of 3. Now, real decision trees can go way deeper. You know, they can be 40, have 40 different splits or even more. And what this means is that these types of models are way, way, way more flexible than our linear model. So if you were to plot this out, it would look like steps. And it can basically make as many little splits as it needs to fit the data as perfectly as it can. So because it has this ability, you know, with a linear model, it's like, here's your equation, figure out the coefficients, but it always needs to be this equation. Always need to think in terms of straight. But for these tree-based models, it really is like, just keep splitting until you fit the data. So they're a lot more flexible and a lot less, you know, restricted in that sense. Now, Curtis has a great question. What do I mean when I say that these terminal nodes are more pure? Well, what I mean is that I say what I mean when I say that is I say that the observations in those final nodes belong to only one of the classes. So we go to like a mixed node here at the top. This looks kind of like Neapolitan ice cream, down to these kind of mono class leaves at the bottom. Other questions? Okay. I'm going to now share my screen again. So now we're going to go from the concept to the practice part. Let's do a little bit of coding here. So what I'm going to do is I'm going to take our model here. I'm going to go make pipeline, and I'm going to put in a couple things. The first thing is I'm going to use not a one-hot encoder. I'm going to use an ordinal encoder. And I'll talk more about why this is tomorrow. But for now, what you guys should just keep in mind is that generally it's better to do ordinal encoding for a tree. So if you're going to use a tree, it's generally better to do an ordinal encoder. And then everything else is going to look very similar. I'm going to put in my simple imputer. And again, my strategy is going to be mean. That's a hyperparameter that y'all can play with. And then the last thing that I'm going to do is I don't need a standard scalar. Because our decision tree looks at each of these features one at a time, it doesn't care whether there's like a big range of values or a small range of values. It doesn't matter. So what I can do is then do a, let's see here, ordinal encoder, simple imputer. I'll do the decision tree classifier. Beautiful. And if we pull up the documentation for the decision tree classifier, there are a couple things that I want to show you. So sklearn, let's see here, decision tree classifier. Excellent. The main thing for now is notice that there is a random state here because, you know, how does it look through all the features? Well, there's a random process at play. So I just want to make sure I set the random state to 42 just so it's reproducible. And then what I'll do is I'll do model DT and I'll do the same thing that I did before. I will just fit it to my training data. And by the way, notice how easy it is to swap in and out different predictors in your pipelines because scikit-learn is like beautiful that way. You can try one predictor, and if it doesn't work, put in another predictor, see if that works. So if I run this here, a couple things. Now, one, you guys are probably asking yourself, what does this decision tree look like? What's happening under the hood here? And one way to visualize what's happening with your tree is to use that plot tree that I talked about earlier. So the way that plot tree works is, let me do PLT. First thing you should probably do is you got to make your figure a little bit better. So I'm going to do fig size equals, this is what I found works best in Colab notebooks, but you might have to work a little bit differently if you're doing working locally. But then you do plot tree, and inside, the first argument that you need to put in is you need to put in the actual decision tree classifier. So how can I grab from this pipeline just my decision tree classifier? What's the way to do that? Is it the steps? You're absolutely right, Carlos. It is the steps. It is the named steps. So what I'll do is I'll do model decision tree dot name steps. And here I'll do decision tree classifier. So that's exactly what I need. And then the next thing I'm going to put, because I don't want to plot out the whole decision tree, I'm just going to plot the first, say, 2 splits. So I'm going to say max depth. And this is the max depth for displaying, not the actual max depth in the model. And then I'll put in the feature names. And because we did ordinal encoding, there are no new features here. So I can just use xtrain.columns. And then just to make it pretty, I'm going to go filled equals true. Okay, beautiful. And I'll put a little semicolon here to reduce the output, the text output. So if I look at this, here is the example of what our decision tree looks like. And we can zoom in a little bit here. Actually, we can't. But if I take a screenshot and drop it in the chat, you can also take a closer look. And what we can see is that the first split that our model makes is along that quantity. So there's that quantity feature. And what it's saying is quantity more or less than 3.5. And that's our first split. And what you can see, and this is represented in the color, you can see that it's able to more cleanly slice off groups from each other. So here we can see that we have like this huge group of, where we basically take everything, almost all of these ones that, almost all of the observations that pertain to our biggest group, our functional group, almost all of them go to the left of the tree, and then almost everything else goes to the right side of the tree. So that's where we see it making that first big drop in impurity. And then we can see that it uses all sorts of other things. On one side of the tree, it uses quantity again. On the other side, it uses water point type. And this goes on and on and on until it gets to those entirely pure nodes all the way at the bottom, which we can't see yet. So this is what our decision tree looks like. Let's see how it performs. If I look at our training accuracy and our validation accuracy, what we can see here are two things. One, we can see that our validation accuracy is even better than with our logistic regression model. But what we can also see is that our training data is up at 99% accuracy, but our validation data is down at 75% accuracy. So what does that mean when you see a big difference between you have really good performance on your training data, but then not such good performance on your validation data or your test data? And Curtis is saying, well, this is a question of overfit, and you're absolutely right. That's what's happening. Because these decision trees, remember, with great flexibility comes great overfitting. These decision trees are so flexible, they can fit the training data almost perfectly, and sometimes that makes it difficult for them to work on data that they haven't seen before. What do we call that? If your model is having trouble doing something, working on data that it hasn't seen before, our model has trouble generalizing. Exactly. And so a really good way to think of these decision tree models is they're kind of like conspiracy theorists. They always see a pattern. They always fit the data perfectly. They know exactly what's going on. But when it comes to generalization, sometimes they can have problems, right? Because they're overfitting to the data. They're seeing signals when really all there is just noise. All right, so let's take our second break, and I want you all to think of any questions, and we'll answer them when we come back. And then let's talk a little bit about what CT and Ben were mentioning, which is hyperparameter tuning. So see you all in 5 minutes. All right, come on back, guys. Okay. So what have we done so far? We made this beautiful wrangle function. We did our splitting of our data. We established our baseline of 54%. We've even built 2 different models, and we found that our decision tree classifier seems to be working better, even though it does have an overfitting problem. And so the next step for us is seeing, can we improve our model performance overall if we tweak a little bit how our model works? So the first, and I think the most important hyperparameter that you need to think about when you have your tree is you need to think about max depth. And max depth means how deep is your love? Nope, it's not the Bee Gees. It is how deep are you going to let your tree grow? So here's a question for you guys. What do you think? So if I set the max depth of my, there we go. If I set the max depth of my data or my decision tree to say 2, what I'm saying is that you can only make 2 sets of splits. So this is essentially, I'm putting a hard stop at how deep my model can grow. And if I set it to 5, well, that means that I'm allowing, I'm not going to split all of these up into 5, but it means that I'm allowing it to continue splitting up to a higher depth. Now, which model do you guys think has an easier time fitting to the data? Which of these options is more flexible? If I only have 3 max depth, or if I bring it all the way to 5 or 6? I think I actually did 6 here. That is to say, as you increase max depth, does flexibility go up or does flexibility go down? And Logan and Curtis and Carlos agree. As you add more depth to your tree, you're allowing it to more closely fit the data. You're letting it put down, I don't know how to do the garden metaphor here, but you guys are absolutely right. So you can think of, if you put flexibility on the XY axis, as flexibility increases, your ability to fit to the data also increases. So with that in mind, what I would like everyone to do is, hold on, let me put us in the right window. What I would like everyone to do is the following. I'm going to open up there we go. I'm going to open up some breakout rooms, and you're going to do some pair programming. And I want you to take 5 or 10, let's say 5 minutes, let's say 10 minutes. I want you to, using the code that we have worked on today, that we've created up until now, I want you to, no, we'll make it 5 minutes. I want you to see, what do you think is the best max depth? How can you, for example, change here max depth to keep this model from overfitting? So what is going to be the ideal max depth here? I'll let you guys decide how you want to do it, but that's what I want you all to do. So in groups, determine what is the best hyperparameter setting for max depth. Pair programmers, go to it. Hold on, let me pause the recording. Pause. That was a really mysterious conversation we just had. Let's now look at those rooms here. All right, so I'll start with 4.
Too many.
It didn't work?
Hey guys, what you working on?
Oh, we're just messing around with the max stuff. Just trying
Awesome.
different numbers out.
Okay, cool. What's your strategy?
First we just wanted to look at the data and see and find a good number, but then we just started throwing out random numbers to see if it would give us a better look.
Okay, cool. What have you found so far?
Um,
No axis named 5 for the object type series.
Yeah.
So how do you actually use max depth?
So for max depth, what you're going to need to do is when you have your pipeline in the part where you have the decision tree, you need to
The random
set that
state, yeah.
hyperparameter.
All right.
So you just put in max depth equals whatever.
Saved fail. Sometime run all.
All right, I'm going to go check on some of the other groups. I'll see you in a sec.
All right.
Hey guys,
Oh, hello.
what are you guys working on?
We're just kind of randomly guessing, and then Chris is wondering if there's a easier way to do like find it so it can match more quickly. Maybe like if there's code, or maybe we have to do a for loop. I don't know.
Okay, good idea.
To show the report of the model, like once it's run, like because at this stage we don't even know how much depth there is, right?
Yeah, I wonder if you look at the documentation for the decision tree classifier, if there's a way to see what the depth is.
Yeah.
All right, I'm going to check on the other groups. I'll be back in a sec.
Sure.
Hey guys, what you working on?
Writing a for loop that's going to make a list of the depth and the optimal, I guess, the difference between decision tree training value and the training value score and the validation score.
Okay.
Are we on the right track?
I don't know. What do you think, Zunaira?
I'm trying to keep along. So from what I understand, the reason that we're saying that it's overfitting is because the training and validation, there's a big difference between the training and validation. Is that correct?
Correct.
So that's what we're trying to fix, that they aren't so far apart from one another.
Exactly.
Okay.
Something like this, Nicholas.
Yeah, I think this makes sense.
And then I would just plot it.
One thing I would do is, I think going up to 1,000, that would mean you have to train your model, whatever, 1,000 divided by 50 times.
Right.
So that would take a while. So maybe just as a proof of concept, you want to start with a smaller range, like say, try 500. So that way you're only doing it 10 times.
Okay.
Nothing more exciting than getting ready for than tuning hyperparameters, right, guys?
That's right. Are we out of time?
No, take your time. I was thinking we would do feature importances, but I think we'll just do them tomorrow. No rush. Okay, so what does this tell you?
It seems like by the time it gets to 50, it's reached it's kind of the difference between the scores, the training and validation scores, is not dependent on the maximum depth after a certain number.
Okay, and so then, Zunaira, based on that, what would be your next course of action?
Okay, so is it possible for us to just work with those numbers where, like you said, after a certain number, it's not affecting it anymore? So can we narrow it down just to those numbers?
Exactly. Yes, yes.
Something like that.
So why don't you do 1 to 50 by 10?
Would 1 to 50 be too much?
Yeah, you know, I mean, I like the idea of narrowing it down. So let's try by 10 and we'll see. It'll certainly save you time.
There we go.
Okay.
So it's
Beautiful.
like a S curve.
Why, instead of doing PLT scatter, why don't you try PLT plot? It'll be a little bit easier to see what's happening. And I'm going to hop around to another group, okay?
Yeah. Yeah.
And we'll come back in around 2 minutes.
Okay.
Good work, guys. Carlos, Kaji, what did you guys find out?
Go ahead, Carlos.
Well, I threw the number 14 in there. I tested it out. What I was thinking with that number was that since we're doing splits in half, I was figuring that I was just gonna go half of 28, which is 14, based on the shape of the train. So I was thinking if the shape of the data is 28 columns, I was gonna go with 14 since a split means it's gonna get split in half. So I went with that number and it didn't work much. So then I kind of play around for a little bit and I saw that 42, the original number, was in a good area. So I kind of play around, and to me, the only number that got over 75.75 was 35 for some reason.
Mhm.
That's
One thing to keep in mind is that when you make that split, you're saying, okay, everyone that's more where the GPS height is more than 3 on this side, everyone where it's less than 3 on this side. You're not splitting the data frame this way by columns. You're dividing up the observation. So you're dividing up the rows.
okay.
Okay. So tell me, what are some strategies that you guys used to help you find your max depth? Why don't you unmute your mics and let's hear. Andrew, do you want to tell me what your group worked on?
Yeah, we used grid search.
Okay. And what did you find?
There we go. Now that I'm unmuted. It actually
Oh, you muted again.
oh, where'd I cut off at?
Very early.
Okay. Yeah, I know I ran into an error, and I know Logan had said he had ran into an error too.
Well, there's no worry about that. We'll be looking more at grid search later. What are some other strategies that people did? Zunaira, can you talk about what your group did?
Okay, so I was working with Ven, and he had tried creating a for loop so that we can try to decrease the overfitting. He was still trying to narrow it down at the end, and we were trying to, so when we did our first for loop, we saw that there was a certain point at which the numbers weren't being affected by a difference.
Okay.
So then we narrowed down the numbers, and it seemed like it came down to, oh, if we don't want the overfitting, it was coming down to like, oh, zero, almost zero depth. And at that point, we just started laughing because I was like, okay, well, then just don't create the tree at all, because then there won't be any overfitting, and that's not a solution.
Yeah.
So we were just messing around with the numbers to see how much depth we can go to get that to go down. But we were working on a for loop and just playing around with the numbers.
Okay. Excellent. I love that idea. Why don't we try to implement that together as a group? So we only have a few minutes left, so I'm going to use a little bit of copy paste code, kind of like a cooking show. I already prepared these onions. All right, and so let's take a look here. The first thing that you can do is that if you look through the documentation for the decision tree classifier, there's a method called getDepth. And so we can see that our decision tree, when we didn't limit it at all, was at a depth of 38. So that gives us an idea of what we are dealing with in terms of the values we want to search for. And so what I can do is, and this is similar to the code that we've done before, which is, let's look at training accuracy and compare it with validation accuracy. And let's do here 38. There we go. I'll do random state. Hold on one second. And no, there's no end jobs here. So let's go by steps of 2, and we'll go from 2 to 38 to see how our model works. And while this is running, so basically I'm just going to make a decision tree model, train it, and then see what the validation accuracy and the other accuracy is. So I'll do, let's see here, Alt and Enter. And then what I'll do is I'll put together a plot. So in that plot, I'll have the depths. So these are all the depths. And I'll plot the training accuracy on one axis, and I'll do validation accuracy on the other axis. And I'll make the training accuracy, I'll make it blue, and then the other one, I'll make it orange. So I'll run all of those, and it looks like this is done. And if I run this out, what I can see is the following. So what is this telling us here? What do we see in terms of the difference between validation accuracy and training accuracy? How do these two curves look different?
You can see there's overfitting after like 12 or 15 max depth.
Right. And so how do you see that? And same question for Joseph. How do we see that?
Your training accuracy continues to increase, but your validation actually seems to get worse.
Exactly. And so what we see is that our model gets better and better at fitting to the training data because it gets more and more flexible. But at the same, and for a while, that seems to work with our validation accuracy. But at some point, there's kind of a level of diminishing returns with our validation accuracy. And then after, looks like this point at around 18-ish, our validation accuracy actually starts going down. So our model is so overfit to the training data that it actually hurts its performance on the validation data. And that's exactly what Carlos is saying. Your validation has this rising slope, and then all of a sudden it starts to go down. And so it's at this point where it starts to go down right here, that's where you see overfitting happening, where your model is so interested in the conspiracies that it sees in the training data that it is no longer able to generalize as well to the test data. So this is kind of one way to build an intuition for it, plotting out your training and your validation metric. And we'll see later in the week about ways to do this differently. What we can do real quick, though, is we can go here to our model and we can just set, let's see here, let's set max depth to 18. And let's just see what happens in terms of our performance. And now that that's trained, I can look at the decision tree classifier here. And what I can see is that while I still have overfitting 90 and 76, notice that I'm able to bump up or increase my validation accuracy by a point because I'm reducing the amount of flexibility that I'm giving to my decision tree model. So by tuning this hyperparameter, I'm able to deal with overfitting and then get better performance. Okay, well, it looks like we've done all sorts of beautiful things here today. Give me 2 more minutes. I promise that I will give you this time back later this week. But what we did is we wrangled our data, our first step, and we had a lot of things that we needed to deal with. We noticed that we had that null island issue where we had zeros or values close to 0 when they should be NaN values. So we took care of that here. We also made sure to set our index to ID. We then needed to drop our constant column, which was recorded, and then we needed to drop both our high cardinality categorical columns and columns that were duplicates of other columns. And then we even needed to have a little if-else statement here so that we could do the same type of wrangling with our training set that we did with our test set. So we had a lot of wrangling to deal with. Then we split our data into feature matrix big X and target vector little y. And we did also a training validation split so that we could get an idea of how our model is performing without actually having to make a submission to Kaggle. We then set our baseline accuracy at 54% and built 2 models, namely our logistic regressor, which performed pretty well, and then our decision tree classifier, which performed a little bit better. And we also talked about why a decision tree, because it's not limited to that linear equation, not always thinking in terms of straightness, right? That it's much more flexible, and that makes it a better model at modeling data that's nonlinear. Now that's good on the one hand, that's not so good on the other hand in the sense that, you know, your decision tree can kind of become a conspiracy theorist and start overfitting to the training data and then having trouble generalizing. And so what we found, the best way to deal with this was to deal with the hyperparameter max depth. And by limiting the max depth, by limiting the flexibility that we gave to this model, we were able to increase the performance a little bit. And we even could talk about and look at this beautiful validation curve, exactly how this works, right? Where your performance keeps going better with your training, but then you'll see it kind of level off and degrade with your validation. We didn't get a chance to do feature importance, so don't worry about that today, but we will definitely check it out tomorrow. So the last thing that I want to show you guys is I want to talk about what you need to do for today's project. So let me pull that up. All right. So the big thing that you need to do is, if you haven't, today is a day to sign up for the Kaggle account. And then from there, I want you to basically work through all of these steps, building your own model. And I want you to create a submission for Kaggle and then do your best to submit it to the site. All right. Don't worry, there might be an assertion error here, or I think the assertion error might be here. Don't worry about that. Don't sweat it too much. Your main goal today is to get to the end of this notebook and put in a submission here in the water pump challenge. All right. So that's it from me, guys. Cece will be doing Q&A today at 2:30. I'll be dropping the link to surprises and confusions right after class. And other than that, everyone stay safe, take care of each other, and we'll see you all tomorrow. Bye-bye.